I will begin. Dear Father, we thank you for this day. I thank you for these students. Just ask you to bless this class today, Lord. In your name I pray. Amen. Okay, so hopefully you guys have some sense of what the general polynomial looks like, right? Is this such a neat construction, isn't it? I mean, it's really neat, I think. But the theorem 32 is sort of the ultimate result there, and it's just this, right? The general polynomial. So what's the idea of a general polynomial? It's like a polynomial which doesn't have any particular relation on the coefficients, right? And so the interesting thing here, excuse me, he mentions there we go, the n symmetric. So this is the general polynomial over the field f adjoin the symmetric function 1, 2, Sn. So this polynomial over the field f adjoin S1 through Sn is separable with or how do I say it? What do you guys? Galois, how's it go? I forgot. Galois. Galois group Sn. It is kind of funny to think about it. I mean, when Galois was alive and then was killed, I mean, it really was during the time of the Wild West, give or take, right? I mean, I guess maybe the Wild West I think of more as like during the Civil War or after, right? I mean, I don't know. When does the Wild West happen? When is that?
Like early 1800s.
Early 1800s?
Well,
because if it's that, then I mean, this you know, we're talking about this silly song, you know, the ballad of, what was it called? The Ballad of Stephanie, is it? Stephanie. Ah, yes. I should put a link in the description of this video. Anyway, so this has Galois group Sn, right? And then he mentions, though, I'm on page 609. He says, this result says that there are no relations among the coefficients of a polynomial of degree n, if there are no relations among the coefficients of a polynomial of degree n. And he says that's what we mean when we say that the SI are indeterminates above. Then the Galois group of this polynomial over the field is generated by its coefficients. Well, that Galois group is the symmetric group Sn. And he says, loosely speaking, this means that a quote-unquote generic polynomial of degree n will have the symmetric group Sn as its Galois group. But he also points out that, you know, okay, great, but is it actually possible to do that over a given field, right? This is not actually possible over all fields. If you're over a finite field, you can't help but have relations between the coefficients, right? Like finite field has so much structure that this is not possible in a finite field. As he mentions, finite fields, every polynomial has a cyclic Galois group, right? Because all extensions of finite fields are cyclic. So that generic polynomials don't even exist in that case. So this is most interesting over Q. So f equals to Q is most interesting. It's always fun when you come up with some sort of elaborate construction in mathematics, but there doesn't even exist an example of the construction, right? It's kind of fun. Anyway, so that's a general polynomial. Now, I'm going to try to talk about some of the substructure. Like what we're trying to do today is be looking at, before I forget, this is kind of out of order in terms of Dummett and Foote, but I want it as a backdrop for what we're doing. All right. So ultimately, last time that I was with you, we got to theorem 39, and I've just sort of proved some of it, probably as much as I'm going to. Theorem 39, what did it say? It said that the polynomial f of x can be solved by radicals, right? If what? Or if and only if what? It's Galois group is what? Is cyclic, is cyclic, yeah. No, is solvable. Yeah, cyclic is, I mean, cyclic would work, but, you know, solvable will suffice. I think cyclic implies solvable, but solvable does not imply cyclic necessarily. All right, so I tried to explain to you this, why this is true. We looked at the example of, you know, the cyclotomic fields, right? Well, we looked at the example of cyclotomic polynomials. You know, example, we looked at we looked like x to the n minus a equal to f of x is, you know, solved by radicals, right? In fact, this was this was not only is it solved by radicals, it's pretty quickly solved by radicals. I mean, I think this one's even nicer because this one had a cyclic Galois group, right? That was the long and short of it. X to the n minus a. So we join the nth root of a, right? And then if the field we're working over already has the roots of unity, then we already generate all the other roots. So you know, adjoining the nth root of a is already Galois. If the field we're working over doesn't have the nth roots of unity, then we have to adjoin them. But once we do, then that's the splitting field for this, and every zero of the polynomial is attained by as part of a root extension. All right, so this was, in some sense, a motivating example for the theorem, right? And I mentioned that. Okay, so other big ideas. Some guiding ideas. The Galois group of f of x, all right, has to be basically some sort of, you know, well, if you'll allow me this abusive notation, it has to be a subgroup of Sn, where n is equal to the degree of f of x, right? And that makes sort of intuitive sense. If, like, the biggest the Galois group can be is the generic case, right? Now, this is all being done over some field, right? And by Sn, I really mean not, I mean, I'm talking about permutations of the roots, right? Automorphisms. Viewing Sn as an automorphism of the n roots of the given polynomial, right? That's the kind of Sn I'm talking about here, literally, right? Not permutations on the numbers 1 through n, permutations in the sense of their automorphisms mapping roots to roots in the splitting field, right? That's what we're talking about here. So that's one guiding idea. What else? The other sort of guiding idea here is that S, and this is technical, but Sn is solvable for n equals to, well, 2, 3, 4. And I suppose n equals to 1 also, but the symmetric group on one thing is kind of stupid. You could throw in 1 there if you want, right? It's a trivial group. Permutations of the identity. Yeah. How many of those are there? So it's solvable for that, right? Meaning that, what does that mean, solvable? Do you guys remember? There exists a chain of subgroups, each of which is normal in the next, and the quotient of all of which are cyclic, right? So that chain of subgroups, which is adjacently normal and has quotients which are cyclic, as we wrote down the other day, And that's not a small, I mean, we could easily spend a whole class working this out, and maybe we should, I don't know. All right? My brother has a hideous handout for this I could share with you. All right? It is a mess. It is just gory calculation. All right? Now, but S5 is not solvable. All right? In fact, S5 is, I think it's simple. It's a simple group. I'm not feeling well today, guys. I'm not thinking quite clearly. I think it's the pollen. Yeah. Just a second here. Let me go back to so he introduces solvable and simple groups way back in chapters 5 and 6, I think. Yeah. I guess I should use I was trying to find you the reference here. Simple. Not semi-simple. I want simple. Simple. Simple group. 103 maybe. Right. So what is the definition of simple group? No normal subgroups? Yeah, well, that's almost right. G is simple if H, a normal subgroup of G, implies H equals to blank or H equals to blank. Yeah, the trivial group or the whole deal. That's right. So what, I mean, Liam's not wrong. A simple group, it doesn't have interesting normal subgroups, right? It only has, which means that it doesn't really allow an interesting factorization, right? We can't form a factor group here except to do what? You can divide by the identity. So basically just wrap the elements of the group in curly brackets, which is kind of silly. Or you can divide by the whole group and just create the trivial group. Those are the two quotients that you can form with a simple group. So simple, it's kind of like atomic, you know, it can't be reduced. And let's see here. Yes, I'm remembering. It's not that S5 is simple. That's not it. A5. A5 is simple. In fact, more generally, AN is a non-abelian simple group. For all n greater than or equal to 5. Now, you're like, okay, well, so what? Well, what was the definition of solvable? Could a simple group be solvable? Why or why not? Why not? Right.
And so then that would require, I guess that would require the
Mm-hmm. So if,
I guess it could be solvable, maybe?
could be solvable. Hmm.
S five isn't, because S five is.
Right. Here, let me see if I can find a clear statement of it for us. I guess I should. Mm. Sorry, guys. I probably should have found this before class, but I thought that you would probably like it more if I graded your test. I'm not wrong, am I? No. Yeah. A word on free groups. It always amuses me whenever I see that title. Ah, now I'm into rings. That's no good. I'm sorry, guys. Solvable. Should I need to take more points off Liam, so you're telling me that?
That's not what I said.
I mean, I could arrange that.
Can I have them?
I didn't really say that.
Come on.
It's a make from my test.
But do please give them to me. If you do.
I'm sorry. Let me just. So suppose it's simple. All right. So if it was solvable, that would mean that there is. How's it go? Starts where? That's my. Is it start at the identity, or which way did the which way did did it?
It starts at the identity,
Uh huh.
and then it goes up to hj, which is equal to g. But here it would just be.
And so we need what?
All of those have to be normal subgroups, right?
I think we need that h. Yeah. For one thing, we need hj, a normal subgroup of hj plus 1. For j equal to 0, 1, 2, da da da, j minus 1, right? Oh, good grief! I'm using j as an index, and as also the total. Come on, not j. Let's say I. Good grief! I plus 1, I equals 0, 2, j minus 1. I think I had s in the definition, did I not?
Yeah, because we had J for the ones over there.
Yeah. So anyway, ranging from the start to the end, they're, adjacently normal, let's say, like this. But there was more, right? Also, what was the deal? hi plus 1 mod hi is what? The quote, was it abelian? Oh, is that right? It's abelian.
I
Oh.
had my a little side note because it's cyclic, but I think that may have been specific to
Yeah, that's right.
example or something we were doing.
Exactly. So we were looking at the cyclotomic one, I think, and in that case, the Galois group was cyclic, which means that cyclic implies abelian, which is what we needed to see that the Galois group was solvable, if I remember right. So, or no, it was. Anyway, the context there was whatever we had was cyclic, so it was implied abelian, and that's what we needed to get solvability. But that's what we need, right? So if we have a simple group, then we can't even, all we can do, right, is E. The only composition series we can form is this. That's it. This is called a composition series, I believe, right? And this is part of a more general story called the program, the Holder's program, if I remember right. which ultimately culminated in the classification of finite simple groups, right? Which is something that happened about 25 years ago or so now. That was the result of about 100 years of abstract algebra, at least. The combined work of thousands of mathematicians, probably hundreds of mathematicians with thousands of pages. Anyway, we do know what all the finite simple groups are. There's a lot of them, but there's a listing. And so if that's the deal, then that means for this to be, there just has to exist such a thing. So this would be, it exists, it's a candidate, right? And, well, E is normal in G. Okay, we got that. But then what do we need? Right, and that means, but G over E is just isomorphic to G again, right? So I guess if we have, does a simple group have to be non-abelian?
Probably, because the definition of normal, if it had any, because if it had a normal subgroup, then that means that, because normal is defined by the inner product, right? Or the outer product, or whatever it's called, like G, H, G inverse, or whatever, and if it's
Yeah.
abelian,
That's just,
then it would just be.
well, what do we know about finite abelian groups? Do we know anything about finite abelian groups? Because that would be what this would be.
So I mean, if it doesn't have to be, but could be, and if the simple groups are solvable, if something's abelian.
My question is,
Doesn't have to be.
my question is, if you have a simple group which is abelian, what is it? What does the fundamental theorem of finite abelian groups say?
Has a normal subgroup. That could be.
All right, I see we need to review. Let's see.
You said I know the fundamental theorem of algebra.
I feel like there was a theorem by this name, was there not? How's it go? I guess we had, I mean, of course we had the fundamental theorem of cyclic groups, right? What was the fundamental theorem of finite abelian groups? Is it not the direct product of Z mod P? Like if I tell you you have an abelian group of order 100, can you tell me the different possibilities? You can, right? Remember? Yeah. So if it's like order 100, that's, what? 2 squared times 5 squared, which means it's either Z100 or it's Z, what is it? Z4 cross Z5 cross Z5, or it's what? Z2 cross Z2 cross Z5 cross Z5, or it's what? Z2 cross Z2 cross Z25, right? Them's your choices. Those are the four possibilities for abelian groups of order 100. Is that right? I believe that's right, right? Yeah. So, which of those have only itself as a normal subgroup? Definitely not Z100. I mean, Z100 has got 0, 50, or 0, 25, 50, 75, or multiples of 10, or multiples of 20, or There's a bunch of subgroups in Z100, all of which are normal because it's abelian. Any subgroup is a normal subgroup because we're in an abelian case, right? You start thinking about it. What can this be? If it's abelian and it only has the identity or itself as subgroups, what could it possibly be? It has to be prime?
That was a shocking mark. Don't take that as a fact.
I think at this point I believe that a simple group can't be solved.
Okay, well, we're not there yet.
You believe that a simple group can't be solvable, yeah. It seems like to get it to be, for this to be abelian, it forces, in fact, G to be prime order, right?
I say that.
I agree with you. I think it has to be prime order, which means it's not just abelian, it actually has to be cyclic, right? So I don't know. It seems like if you had a cyclic group, so I feel like I've sometimes said that simple implies that it's not solvable. Maybe that's wrong. Maybe I have to say a simple group which is not cyclic is not solvable, right? Like cyclic group is kind of a trivial case in some sense, so we should set that aside. So setting aside cyclic group, if you have a simple group which is not cyclic, then it's not solvable because this. All right? So now, how about if A5 is simple, is A5 cyclic? Definitely not, right? Permutation groups are not cyclic. They have multiple subgroups of the same order. They're definitely not cyclic groups. All right, so that's just kind of a backdrop. The reason that we don't have a generic formula for finding the zeros of a polynomial, past order 4 is past order 4, S5 has inside of it a subgroup, in particular A5, which is a simple non-cyclic subgroup, which is therefore not solvable. Which means that if your polynomial has A5 as its Galois group, it does not allow for its roots to be found in a root extension, which is to say that the solutions to that polynomial equal to 0 are not of the form like a quadratic equation. They're not formed by roots of the coefficients plus some algebra steps, yeah? So I felt like we should spend some time talking about the background group theory because that's kind of something we didn't do in the previous course, right? But at the same time, I will not bore you with the 2 hours of gory cycle calculations it takes to prove that. Although I do have a handout from my brother with the details if you want to see it. Okay, so let's look at this example. So if we look at f of x equal to x to the 5th minus 6x plus 3 over the rationals. So understand that the Galois group of a generic polynomial being Sn shows that it's possible. It doesn't show that it actually happens, right? We actually need to find a specific polynomial to exhibit that there exists a polynomial which takes, A5 as its Galois group. All right? So let's try to look at the details of that. This is such an example. So let's work it out. So this is page 629. I'm trying to work through this example right now. So to start with, can you guys tell me why it's irreducible? Eisenstein, yes. P equals to 3, right? Then what's next here? He says the splitting field K for this polynomial therefore has degree divisible by 5 since adjoining one root of f of x to q generates an extension of degree 5. All right. That makes sense. So if f of alpha equals to 0, so to speak, then q adjoin alpha over q yeah, that's 5, right? Because we just proved it's irreducible, so that's a degree 5 extension. Yeah, I mean, come on. You remember what we already know. Good grief. So then what? He says this, but now that doesn't have to be the splitting field, right? That's the thing. Q alpha might not be splitting field, right? And, not to beat a dead horse, but x cubed minus 2 is in qx, right? But q adjoin the third root of 2 is not the splitting field. So, I mean, we know this. If we adjoin one root, it doesn't necessarily get the splitting field, right? So q adjoin alpha doesn't have to be the Galois extension here. All right. But we do know this, that the Galois group has to be a subgroup of S5 of order divisible by 5. This is the Galois group of f of x here. This is a subgroup of S5 with the order of the Galois group. Divisible by 5. Does that make sense why it has to be divisible? Why does the order of the Galois group have to be divisible by 5? Can you guys tell me? Mm-hmm. So you're like, if we think about the splitting field, let's call it K, right? And so Q adjoin alpha is at worst an intermediate field, and at best it's equal to K, right? And then there's Q down here. And then we have the fixed field correspondence, right? So like K corresponds to the identity, right? And this corresponds to, I don't know, subgroup, right? And this corresponds to the whole Galois group. I keep forgetting how to mispronounce it. Galois, the whole Galois group. And we know that the fundamental theorem of Galois theory says that there's a connection between what? The index of the intermediate field and the order of the extension of the intermediate field and the degree, the index of the subgroup, right? So this H has index 5 because this Q alpha has degree, I mean, this is a 5, right? So this is a 5 is what I'm trying to say. The index of the corresponding subgroup, right? The subgroup for which Q adjoin alpha is the fixed field should be, I think that makes sense. So that right, and so if that means the order of the Galois group should be divisible by 5, right? Because, well, Lagrange's theorem, right? The order of a subgroup has to divide the group. I think that's, well, anyway. So then, what does that mean? We have that the order of the Galois divisible by 5. What's that mean? Remember our group theory? What does it mean if you have 5 is a divisor of the order of the group? What does it tell you about the group? P divides the order of a group and P is prime, what does it tell you about the group? This implies that the Galois group of f of x has element of order 5. So I think this was, I want to say this is Cayley's theorem. I may or may not have proved this in class for you guys in your defense, but I mean, we know that if you have a group that has order P, it's cyclic, right? But if P divides the order of the group, I think this also implies that there exists a element of order P. I'm trying to find that. I'm trying to find where it is. It should be before the before in the CeLo theorems in here. It's one of those things we prove with the conjugacy group action and such. What's that?
That's what I'm doing the presentation on today, and I thought that sounded familiar, but then I thought I was wrong.
Ah, no, you're not wrong. All right, I'm sorry. I just all over the place today. Or 118. I remember this being Cayley's theorem. I might be wrong, but where is it? Ah, come on. Oh no, that's not the one I'm looking for. You know that Cayley, he did too much. Oh, maybe I'm thinking Cauchy's theorem. No, Cayley's theorem is every group is isomorphic to some subgroup of the symmetric group. Yeah, that's not it. I think it might be Cauchy's theorem, actually. Yeah. Right, like, yeah, saying the result is due to Cauchy, it's kind of like, well, it could be worse. It could be due to Gauss, or the worst would be Euler, right? Oh, it's due to Euler. Well, thanks. Which of his, yeah, like 5 people did everything. That's not so far from being wrong. Oh, come on. Cauchy is not even in the, oh, Cauchy's theorem, 93, 96, 102, 146. 93, 96, 102. Thank you. Proposition 21, it is Cauchy's theorem I'm thinking of. Proposition 21 on page 102 says the following. If G is a finite abelian group and P is a prime dividing the order of G, then G contains an element of order P. I don't want to assume abelian. Curses. We don't know this is abelian. Man. Oh, although Cauchy's theorem is valid for arbitrary groups, see exercise 9 of section 7.2, the following is a good example of the use of blah, 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 blah. So in other words, this proposition 21 is unnecessarily specialized just to make the proof simpler. Not in the technical sense of simple, but in the sense of being lazy to prove. Because he says on page 101 that Cauchy's theorem is actually true for non-abelian groups just the same. Okay. So it has an element of order 5. And our time will run out here. Ah, our time is running out. So that means it's Galois group. So if you have an element of order 5 and your subgroup of S5, what's that mean? I'm going to call the Galois group G for the sake of not writing Gal a bunch of times. This means G has a 5 cycle, right? Because the only way you can get an element of order 5 inside S5 is something like 1, 2, 3, 4, 5, right? You can't build something of order 5 from multiplying lower degree cycles, am I right? Think about it. So it's got to have a 5 cycle. And then what he does is he points out that f of minus 2 is equal to minus 17. f of 0 is equal to 3, f of 1 is equal to minus 2, and f of 2 is equal to 23 rather.
And that is obvious.
Plugging them in.
Yeah. Oh.
And so make a graph what's going on here. At minus 2, it's minus 17, right? Down here, right? At f of 0, it's 3. At f of 1, it's minus 2. At f of 2, it's 23. So, I mean, I'm not sure that's actually where it turns around, but it's got to look something like this, right? So you can see from that and basic calculus, which he uses to affirm the thing I'm about to say, this polynomial has how many real roots? 3. Well, this polynomial has at least 3 real roots. We don't know, I mean, we don't have enough information to see what happens elsewhere, but if you differentiate this, if you look at df dx, you get, 5x to the 4th minus 6, yeah? And if you set that equal to 0, what do you got? I think you get plus or minus the 4th root of 6/5, which says that this can only have turning points where? Basically, within plus or minus 2, this polynomial can have turning points. Outside there, it can't turn around, which says that that's everything interesting. Past that, it doesn't turn around. That means that there are only 3 real roots to this polynomial. Does that make sense? And then, knowing that, it follows then that the other, hey, shut up. The other 2 roots then have to be what? They have to be complex, right? And so the Galois group does what? It permutes the roots of the polynomial. So if there's a complex root, that means it's going to permute that root and its conjugate. They come in a pair because it's a real polynomial. Figures. So what I'm trying to say is that there's a permutation which will act as complex conjugation and move that one pair to the other. So that says that the Galois group contains a 5-cycle, and it also contains a 2-cycle, which is the complex conjugation. But once you have a 5-cycle and you have a 2-cycle, then by the bunch of group theory that I haven't covered, that implies that you have all of A5, which is an example of a non-cyclic simple group. Therefore, this polynomial is not solvable. It does not have a solvable Galois group. You cannot write a formula for the roots of this polynomial in terms of in terms of roots. So this proves the insolvability of the quintic, that there exists a polynomial for which there's no generalization of the quadratic formula. So what I'll try to do next time, you guys, is dig into the classic cubic formula and the Cardano's formula. Try to look at the discriminant and see if we can appreciate some of the, things that Lagrange did and so forth. Does that make sense? Well, I don't know if it makes sense or not, but that's what we're doing. Thanks, guys. Sorry I was so late today. I'll try to get started on time next time.